All right. So what we are trying to do here is we are trying to do a 2-bit adder, right? So a 2-bit adder basically means that's kind of our physical description of what it is we are doing. We are taking two numbers, each one 2 bits. A1, that's one number, and this is an oops. And we usually write the most significant first and least significant next. So this is the two numbers we want to add. When we add these two numbers, we're going to get a result, which is sum 1 and sum 2, right? And an example of number would be, this is a 2-bit number. This is another 2-bit number. We add them, and the sum is going to end up being that. So this is kind of the physical description. So what we want to do from a system diagram point of view, we've got two 2-bit numbers coming in, A and B, and we're getting a sum coming out, which is a 3-bit. Oops, it's a 3-bit number called sum. Okay. And the zeros and the ones are binary numbers, so we don't have to describe what they mean. Okay. So that's not too bad. Now, you could, if you wanted to, basically do a truth table that looks like this. You can, so this would be what I would call a, solve the whole thing as one big problem, normal approach. Let's call it normal approach. And what I could do, I could say, okay, my inputs are A1, A0, B1, B0. These are, and then make a truth table of this with sum 2, sum 1, and sum 0. And then for every number I add, I say, okay, 0 plus 0 is 0. And then keep going down the list and all the way up to 1, 1, 1, 1, which gives me 1, 1, 0. 3 plus 3 is 6. Okay. And fill it out. Then I can do a K-map for S1, S2, S3, design them, and be done. The problem with that is this problem gets really complicated now, but the 2-bit is almost manageable, but it's difficult. But for a 3-bit, 4-bit adder, 5-bit adder, 16-bit adder, it becomes really, really difficult to do. So we're using this one for our lab to give you an idea of you can actually do a modularized design, even though there are more steps, the end result is simpler. Okay, so what we do in step 1, we design a half adder, and the reason they call it a half adder is because it only needs to take in just 2 numbers. It doesn't care. There's no carry in, because what the half adder will do. The half adder will only take care of the least significant bit, which has no carry in coming in. So all it has to do from a system diagram, all it has to do, it has to accept 2 bits, let's say A0 and B0, and just give us a sum 0 and gives us a carry out 0. That's all it has to do. So this is the half adder we're designing. Okay. Once you've designed it, then you can just use that box in your next circuitry and make it look like, I don't have to do it again because you already know how I do it. So to do this one, then all I have to do is basically say, okay, I have an input A0, B0 comes in, I get a carry out, and I get a S0. So I get a 0, 0, and I get a 0. I get to add 0 and 1, and then 1 and 0, and 1, 1. Normal truth table business. So you get a 1, you get a 1, and you get a 2. You look at this, and you say, oh, look, this is pretty easy. I don't have to do any K-map or any silliness. It's pretty obvious. That's a basic definition of a gate, because C0 is simply A0 ANDed with B0, right? You see that?
Yes, I do.
Okay, perfect. So now, then you say, oh, then what is S0? Oh, S0 is just simply A1 ANDed exclusive OR with B1. because B0. Because anytime the bits are different, I get a 1. Anytime they're the same, they get that's the definition of exclusive OR, right? So now the next thing I need to do is do a schematic of this thing. And basically, you can go through the formal process of ID blocks and all that for this. So we should probably do that just to be clean. So we say, okay, here's a nice schematic for this thing. And all I have A0 coming in, and I have B0 coming in. Okay. B0 coming in. And all I'm going to do, I'm going to take A0 and B0. I'm going to AND it together, and that gives me C0. Okay. And then I can take A0 and I can take B0 and I can exclusive OR them together. And then I'm going to get S0. Okay. And of course, you got to go do your ID block, and you're going to ID block. And then the component block, put the pin numbers. And whatever, let's say call this one U1 and U2. You're done. You basically have designed a half adder. You're done with that. The next thing you need to do, the next step in the process is you do a full adder. Okay. And since now you know how to do a half adder, in the future, you don't have to draw what's inside the half adder block. You can just drop it into your circuit, and you say, go back and look at, the reference that I just gave you earlier. So the next thing you need to do, which is a little bit more complicated, is you need to do the full adder. So the second step in the process is to design the full adder. And the only difference the full adder has with the half adder is because when you have your full adder sitting here, not only you have the two bits coming in, A1 and B1 coming in, you also have another carry from the previous bit that comes in. Okay, we call it carry 0. So I'll bring the carry 0 in here. And then what comes out of here is the sum 1 and sum 2, or we can call this one carry out. This is basically carry out from this one, carry 1. Okay. But this, if you don't have any more bits to add, this becomes your sum 2. Okay. Does that make sense?
Yes, it does.
Okay. So now what we need to do, we need to go here and do the same thing we did over there for just this little module. And this case will be A1, B1, C0. And then I'm going to call it S2 and S1 just to make it customized to ours. But obviously, if I was doing this for a broader market, I would give them a generic name that people can use. But since we're only using it for our design, I will just give it the name that is meaningful to us. So here, the design becomes a little more complicated because now I have 3 input. So I have to do more. Lines. So the process is again simple, right? All you're doing, you're adding 0 plus 0, and if there's a carry, you add to it. So that would be a 0, that would be a 1, that would be a 1, that would be 2. 1 plus 0 is 2. This becomes a 1, 2, 2, and then finally 3. No, not 1 plus 1 plus is 3. Okay. So this is the case. This one, I can't just look at them and say it's one thing or the other. So what we'll do, we have to do a K-map for it, okay? So we have a K-map for let's say S1, and then later on we'll do a K-map for S2. So this is A1, B1, C0, and by now K-maps are kind of old hat, right? So 1, 1, 1, 0. 0, 1. And so now what we have here is we have this setup. So we'll take these things and put them in there. So for S1, this is 0, 1, 1, 0. So we're here, 1, 0, 0, 1. Okay. Did I do that right? Yeah. Now, this pattern, when you play with it a little bit, you can write the equation, but if you write the equation without seeing the pattern, it's going to be a pretty complicated, lots of gates, because each one, the prime implicants are pretty small. But whenever you see a pattern where every other is one, that typically means what you're looking at really is an exclusive OR. And the exclusive OR for S1 is basically going to be A1 exclusive OR with B1 exclusive OR with C0. So far, so good?
Yep.
Okay, so now the next thing we need to do, the next process is to figure out if we can figure out what S2 is, and then we are home free once we've done that. So S2 will do the same thing for this to find out what S2 is. And S2, same deal, A1, B1, C0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And then that one is 0, 0. I'm basically going through the S2 column and writing them down. Unfortunately, I don't know any tricks to make this any easier. This one, basically, when you go do it, there's a prime implicant here, there's a prime implicant here, then there's a prime implicant here. So you're going to have a bunch of terms you have to implement. So this is going to be basically A1, B1 for the horizontal one right here, or for this one is going to be B1, C0, or for the one on the bottom is going to be A1, C0. That's about as simple as we can get this one, I think. So now what we could do is for a full adder, if somebody asked us what, we got to do the schematic to be complete. So if somebody wants to use it, they know how to use it. So what we're going to do is do the same thing. So, and notice for these, you don't need to use the switches because you're implementing a module that's going to get plugged into your full design. You're not going to implement them by themselves, so you don't have to do the switches in here if you're wondering. So here, the inputs to the system, and inputs always come in on the left-hand side of your schematic. So the inputs through your systems are A1, B1, and C1. And typically make life easier if you just draw a line straight down for these. And then to create someone, you just basically, and we're going to have I'm going to only use two input exclusive. No, what were they get? Yeah, exclusive word. Since there are two inputs, I have to use two to make it three things. So what comes out of here is my S1, because remember what it was? It was basically three things exclusive or with each other, and I just did it. And then the next thing we need to do, we need to build that. Well, that's not too bad either. So because what I will do is a little more didn't want to do that. So what we'll do, we'll take A1, we'll take B1, and exclusive OR them together. My apologies, this is actually a C0 coming in here. I wrote that C1, that's not what it is, C0. The inputs are A1, B1, and C0. So that's one. Then I have to do A and C and since I have two inputs devices only, I have to do a couple of OR gates as well. And then the final one is B1 and C0 ended together. And of course, this you put it in a schematic format as well with the component block and an ID block, and then pin numbers, let's say 1. Oh, we already use 1 and 2, 2, 3, 4. 4, 5, 6, and I think we call this one U2. And this we already had a U1, whatever. You can go through and do the right thing for the schematic. If there are other videos that talk through how to do schematics. Now, what I have done, I have module. I know how to build half adder and full adder. Now I'll go to the full circuit and say, okay, now for my final steps, I'm going to put it all together. So I'm not sure what I'm doing, so let's go ahead and move this over. So for the 2-bit adder, which is the reason we are doing this one, for the two, let me zoom in so it's a little easier to. So for the 2-bit adder schematic, I do the whole thing. I say, okay, I've got a switch. So we're going to call one of these guys A1, one of these guys A0, one of these guys B1, one of these guys B0. Okay, so this is where our inputs is coming in. And then we have our half adder, which we don't have to show what the circuitry is inside because we have another schematic that does that. And our half adder basically takes A0 and takes B0 and then produces some 0. There it is. And then for this one, for the full adder, basically the carry for here goes to here because the carry generated for the least significant bit is fed into the second bit. And then A1 comes in here and B1 comes in here. And this one, what generates is S1 and S2. Okay, so now our adder is done. Now we have a binary number, but we want to take that and display it into a 7-segment. And in lab 4, before you got to this point, there was another experiment that showed you how to take binary number, put it in a, I forget, is it 4511?
Yeah. Yes, it is.
4511 HC chip. And when you do that, then basically take this one, put it in the least significant bit, put this one in the next significant bit. So let's say data 0, data 1, and this goes to data 2. And if you remember, that chip accepts 4 bits. So the 4th bit, you got to ground it because this only goes to 6. So 6, if you write it in 4-bit, the most significant bit is always 0. And then you have your 7-segment display sitting here. And they have pins that are called A, B, C, D, E, F, G. So A through G, and they have an A through G. And of course, you put the pin numbers here. And then there are a couple of other pins. You got to read the data sheet and make sure you set the control pins such that you're operating this one, like there's an enable chip and there's a light chip, a light pin, and things like that you have to set. And of course, you have to have the VCC connected and ground connected and all that, which I'm not showing. Of course, I'll just go ahead and put this schematic. There's going to be a component block where it says this is U, whatever. This is another U. This stuff is modular, so you don't have to say that. And then there's an ID block here. Okay, And so that is, then you're done. That's it. That's what you build on your board, if you have the board, if not on Tinkercad or some similar simulation system. And hopefully as you flip the switches, you should get the sum of those things. So for example, if your A is set at 2 and B is set at 3, you should get a 5. So this thing should light up and you should be reading 5. If this is 2, which means this switch is open, this switch is closed, plus 3, which means both switches are open here. So you're getting a 3 out of B, and you're getting a 2 out of A. Add them together, and you should be seeing a 5.